In order to evaluate the Fourier transform on a computer, we are going to have to sample our function in the time domain. Not only sample, but we'll be dealing with quantized values as well. We are using a digital computer. And then when we do our calculations in the frequency domain, we'll also get corresponding samples there, because we can't calculate or transform for all possible frequencies. This leads to a sequence transform known as the discrete Fourier transform. We'll talk about it here in terms of approximating the Fourier transform. So this is the same x of t signal that I used last time, and then let's assume its Fourier transform has a shape like this. This is x of omega. Again, this has a duration of tau. I know that sampling x of t, so again, let me draw the general shape of x of t here as a dashed line, and I'm going to sample this. I'll use ideal sampling in this case, where my samples are capital T apart, and we call this x bar of t, my ideally sampled signal. And then Fs here, our sampling frequency, is 1 over t. And I can only evaluate a finite number of samples, or samples out over only a finite interval. So I'm going to call my sample interval here, the duration of my sample interval, I'm going to indicate that as t0. So for our ideally sampled signal, the corresponding spectrum, you know what that looks like. Just going to get replicas of this baseband spectrum, and my replicas are going to be Fs apart. So I'm actually going to use F here instead of omega, slightly more convenient. And it's the sum of all these replicas. So I get another replica here at 2Fs. Okay, and these are all going to sum together. Another one at minus Fs, minus 2Fs. So this is the corresponding spectrum of x of omega. Now, based on the work that we just did, I know that, let me sketch the outline of x bar of omega here from above. So it looks roughly something like this. And actually I'm going to include a scale factor here. 1 over t0, x bar of omega is this dashed line. I know if I now sample this in frequency, and these samples are 1 over t0 apart, and then this will repeat at Fs, which is equal to 1 over t. Then I know what I get back is a representation, a periodic extension of the sampled version of x of t. So what this will transform back as is, let me draw the outline for x of t. But what I'll get back is not my original sampled version from the plot above, but the periodic extension of this. So I'll get back samples, including 0 samples there in between these replicas. And again, this goes on in both directions. So I'll get back this sequence of values. This distance between replicas is t0, and again this duration of the non-zero duration is equal to tau. There is a relationship between t0 and t that gives me the number of samples that I'll have then in sampling x of t. That's going to be t0 over t. It also turns out to be exactly equal to fs, my sampling time, over the interval between my samples in the frequency domain. So the sequence I get back, x of n, is going to be approximately equal to, the reason it's an approximation is that aliasing will be present, but if the aliasing is small, then the sequence I get back from this series of operations is going to be approximately equal to a sampled version of x of t, and then the sequence I have representing the amplitudes of these impulses in the frequency domain, I'll call this x of r, where r is my sequence index, is an approximation to 1 over t0 x of n omega 0, where omega 0 is 2 pi over t0. Can show that x of r is equal to the sum from 0 to n0 minus 1. Now notice here the summation is not over, does not extend from minus infinity to infinity, but just over the samples that make up this one period of this periodically extended function in the time domain, j r omega 0 n, and this is called the DFT, the discrete Fourier transform. So it allows me to calculate a set of complex sample values from samples of my original x of t, and then there is an inverse transform, x of n, that's 1 over n0 sum from r equal to 0 to n0 minus 1 of x of r e to the j n omega 0 r. This is the inverse DFT, where n0 is t0 over t. It's the duration over which I'm taking samples divided by my sample interval, and then the discrete time frequency that appears here, capital omega 0, is just 2 pi divided by n0. Okay. Let's talk a little bit about choosing appropriate values for t and t0. Okay. So t is my sampling time, and t0 is the interval over which I'm going to take samples. So we know from the Nyquist criteria that our sampling frequency has to be greater than twice the bandwidth of my signal. Since f of s is equal to 1 over the sample time, then I get that t has to be less than or equal to 1 over 2b. So this is our sampling time. And it's determined by the highest frequency present in my time domain signal. So again, if B is something like 10 kilohertz, then I need to sample at a minimum of 20 kilohertz. We also know that there's a relationship now between the distance between my x of n samples and the distance between my samples and the frequency domain. T0 is actually, this is T0 is the total time duration in the time domain, and F0 is the frequency between my frequency samples, also called the frequency resolution, where F0 is the desired frequency resolution. So if I want, for example, 1 hertz resolution, I need to calculate. I need to gather 1 second's worth of data, and if I want to preserve, if the bandwidth of the signal is 10 kilohertz, then I need to sample at least a 20 kilohertz rate, and then so over 1 second, that would be 20,000 samples. Finally, we have this relationship for the number of samples then that would be gathered. It's the total time duration over which I'm gathering samples divided by my sampling interval. So this determines the limit, the number of samples I'll have in both the time domain and also in the frequency domain. And we indicate that with the variable n0.